Hello everyone, I'm your teacher Terry, and in this video I'm going to show you how to go through some intermolecular force problems on specifically organic molecules. So hopefully it'll help you answer some of these questions on an exam. So without further ado, let's begin. We have this fluoromethane, CH3F, and methanol, CH3OH, have approximately the same molar mass. Okay, so these approximately the same molar mass. You could add it up if you want to take your word for it, or take their word for it. However, the boiling point of methanol is 65.15 degrees Celsius, whereas the boiling point of fluoromethane is almost 100 degrees lower, negative 78.4. Explain. Okay, well, we should look at these compounds. So fluoromethane, whoops, it's just one hydrogen here, is like this. We have a polar bond that strongly points towards the fluorine. But with methanol, we have COH. And yeah, we have polarity between the carbon and the oxygen bond as well. But most importantly, this OH can hydrogen bond. So this is the strongest type of intermolecular force of the three, generally speaking. So it's stronger than, so stronger intermolecular forces. So it causes stronger intermolecular forces than kind of our dipole forces from the C8, from the CF. Dipole, from the dipole forces from CF. And I just wanted to highlight so that what these intermolecular forces are. So we have a delta positive on the carbon, delta negative on the fluorine. If you have another one of these molecules, say a fluorine, maybe I'll put it in blue so it's easier to see. A fluorine here, carbon here, H, H, H. We have a delta positive on this carbon, delta minus on this fluorine. So we see some bonding between these two due to these permanent dipoles. But with methanol, we still have dipole-dipole bonding, but it's dipole-dipole bonding intermolecular forces of hydrogen that's bonded to an oxygen. And if a hydrogen is bonded to an oxygen or a nitrogen or a fluorine, then those intermolecular forces are very strong. So this is the intermolecular forces between a molecule here. Delta positive on the hydrogen, delta minus on the oxygen, and these hydrogen bonds are so much stronger. Because they're stronger, it takes more energy to break the bonds between molecules. So they'll be at a higher temperature. The boiling point is where the atmospheric vapor pressure equals atmospheric pressure. So we need enough energy, we need a high enough temperature in order to break these bonds so that they can go into the gas phase. Well, it's a lot harder to break these bonds if the intermolecular forces are stronger. Here we have weaker intermolecular forces, so the temperature is a lot less in order to break these bonds to go into the gas phase. Okay, so that one's done. Let's go on to our next question here. So number 2, predict which liquid of these four will have the highest vapor pressure. So we're going to neglect molar mass differences in molar mass. Explain with reference to intermolecular forces. And so see definition for vapor pressure. So if you're not sure what vapor pressure means, then please go back. I do have a video on that, on vapor pressure. But vapor pressure is essentially the pressure of the gas, of the liquid. It's the pressure of the molecules in the gas phase that are above a liquid, essentially. So if we look at this compound here in A versus B, C, and D, Which one will have the highest vapor pressure? Well, the highest vapor pressure means the most pressure in the gas phase. And in order for it to have the most pressure in the gas phase, we need more molecules in the gas phase. So more molecules is more pressure for a given temperature. And this is all at room temperature, so the temperature is the same. In order to get more molecules, we need to break the intermolecular forces or the intermolecular bonds of the molecules in the liquid phase. So when we break these intermolecular forces in the liquid phase, we break the forces between the molecules so that they can escape into the gas phase. So which ones have, if we have the most pressure, then we need to break the most intermolecular forces, or intermolecular bonds, which means we need the weakest. If we need to break more, then we need those intermolecular forces to be very weak. We need to break those bonds quite easily. So we're looking for the lowest intermolecular forces between the molecules. So if we look at this molecule, just think of a million of these molecules together, and they're stuck together from intermolecular forces. What's causing them to stick together? Well, there's a dipole here, so we have dipole-dipole intermolecular forces. And then we also have this nonpolar section, which can add London dispersion forces, and it's not branched. So we have two types here. If we look at B, we have no dipole-dipole. We only have London dispersion forces that exist. So this one's going to be a lot weaker than this one because this one has dipole-dipole forces. So B is going to have lower intermolecular forces than A because the dipole-dipole interactions are going to increase the intermolecular forces. Now, if we look at C here, we have London dispersion forces, but we have this OH group. And whenever you see an oxygen and a hydrogen bonded together, we can have hydrogen bonding. And these cause strong intermolecular forces between other molecules. So if you imagine a bunch of these molecules around each other, they're going to be stuck together a little bit more stickiness because of the high intermolecular forces from the hydrogen bonding. So this one's out. Whoop. So that one's out. And then this last one, part D here, same thing. We have this hydrogen bond, OH hydrogen bond, which makes it strong as well. So that one's out as well. So the one with the lowest, I'll get the right one here. The one with the lowest intermolecular forces has the highest vapor pressure. Okay.